So this lecture we begin a new chapter, the chapter on current mirrors. This lecture and next lecture will be about current mirrors which are used to bias uh, amplifier circuits in integrated circuits as well as to achieve bias stability. So let us begin by talking about bias stability. As you know, bias stability in amplifiers refers to maintaining the collector or a drain current, depending on bipolar or MOSFET, of a transistor constant. So you want to maintain the drain current or collector current constant when temperature and process vary. Alright, so you're familiar with this concept, I'm sure. In MOSFETs, process and temperature variations cause variations in threshold voltage, mobility, and device dimensions. So, process variations cause changes in VT, mobility, and device dimensions. Temperature variations cause changes in VT and mobility. Of course, the temperature doesn't affect device dimensions. Now, the reason threshold voltage and mobility vary with process as well as temperature is because of their dependence on doping or doping density. And now during fabrication, the implantations that are done to design for the threshold voltage, the exact amount of implantation that occurs in any small area of a single die actually varies from one place of the die to another, and that causes variations in VT. And the mobility, of course, is a function of doping density because of impurity scattering, and so mobility also is a function of process variations, and of course temperature. Now in discrete circuits, you all must be familiar with this circuit. Bias stability is achieved by negative feedback in general, and in the specific case of this circuit, it is achieved by putting this emitter resistor, which causes the negative feedback and makes the collector current relatively independent of variations in temperature as well as variations in beta, which are caused by process variations. Now, in integrated circuits, resistance values are far less accurate, and so they are not nearly as widely used for bias stability. But there is one property that integrated circuits have that discrete circuits don't have, which is that it is possible to fabricate transistors that are nearly identical. That is possible only when they are placed close to each other on the chip, but at least it is possible. So in MOSFET integrated circuits, bias stability is achieved by utilizing such identical transistors. So let us look at this our common source amplifier, and this time I am applying the input at the PMOS gate, and so the NMOS acts as a load, and it is a current source load which we have seen provides the highest output resistance, and therefore this circuit provides the highest gain. Now as temperature and process vary, the threshold voltage and the mobility of this NMOS vary, and therefore its drain current varies. So the idea of this M1 is that it is a current source load. It is designed to provide a constant current to the driver transistor. But because of temperature and process variations, mobility, VT vary, and so the drain current does not remain constant as a function of process and temperature. And we want to achieve bias stability, we want the drain current to remain as invariant as possible with process and temperature. So this is where current mirrors come in. So let us look at this simple current mirror circuit. In fact, this circuit is called the simple current mirror. So let us look at it. Let us look at the structure first. So this M2 is the transistor. So let's go back. So this numbering is a little confusing, but this M1, the role that this M1 is playing here is the role that this M2 is playing in this circuit. So this is a generic load that is connected to this NMOS, and in our common source amplifier this would be the driver transistor, the PMOS. So now here, instead of applying a DC gate voltage at M2, we connect this additional circuit. What is that circuit? It is a current source connected to a diode connected transistor, so that the diode connected transistor is forced to carry this current IRF. Alright, now let's look at the equation. So for M1, we can write the drain current of M1, which of course equal to IRF, equal to the saturation region current or MOSFET. So incidentally, because M1 is diode connected, it is always in saturation. So we write this equation. For M2, for now, if we assume that M2 is in saturation, then we can write, and I've called this IO, the current through M2, O for output, as mu1 Cox by 2 W by L2 Vg1 minus Vtn squared. So this is W by L1, this is W by L2. The gates of M1 and M2 are shorted together. The sources of M1 and M2 are shorted together. So the gate source voltages of M1 and M2 are equal. So now if we divide these two equations, we'll do I0 by ID1 or I0 by IREF. Then if we divide, then the mu1 Cox by 2 cancels, Vg1 minus Vt cancels, and all we get is IO is equal to W by L2 divided by W by L1 into IREF. So this we say then that M2 mirrors the current of M1 with some factor which is determined by only the geometrical dimensions of M2 and M1, and so this circuit is called a mirror. Now let's make some more observations about this circuit because it is such an important circuit. So the principle of current mirroring is that we place two transistors, two identical transistors. So did I mention that? Yeah. So M1 and M2 are identical transistors except for their widths and lengths, and they are placed close to each other on the chip. And identical means that they have the same threshold voltage and they have of course the same mobility, assuming that they are close to each other on the chip. Alright, so the way we make a current mirror is by connecting the gates of two transistors together and connecting the sources of two transistors together, and in fact grounding the source terminal of the two transistors together. Now as we just saw, I0 is independent of Vt as well as mu1, so it is dependent only on these three parameters, alright, the W by L ratios and IRF. Now of course on the chip, because of process and temperature, Vt will vary, mu1 will vary for M2 as well as for M1, but because they are identical transistors and because they are placed very close to each other on the chip, the variation in Vt and mu1 for both transistors will be the same, and because it will be the same in these two equations, when we divide, we are able to cancel the Vg minus Vt terms and the mu1 Cox terms. Alright, so the beauty of this circuit therefore is that even when Vt varies, the current I0 does not vary. Unlike the case where, so let's go back again, we had connected a DC voltage source here. If you have a DC voltage source of a constant value, then as mu1 and Vt vary, the drain current varies. So now in fact from another way of looking at this circuit is to say that as the temperature and process vary and Vt varies, Vg1 varies along with Vt so that the current in both the branches remains constant. So in fact, because we are forcing a constant current here, if Vt varies, Vg must vary so that the same current continues to flow, and because M2 mirrors the current of M1, the current I0 flows here independent of the value of Vt and mu1 as long as the Vt and mu1 are equal for both these transistors. Alright, one more thing to note is that although here the current is shown as varying as a ratio of the W by L ratios, we know that the suppose L2 was different from L1, then the fact that L2 L1 are different causes the VTs to be different of M1 and M2, because the VT depends on the length of the transistor. So if you want to achieve this equal threshold voltages for both the transistors, then we must keep the lengths of the two transistors also the same, so that the lengths in fact will also cancel, and so I0 will be W2 by W1 into IRF. So almost universally, when one makes a current mirror, the lengths of the two transistors are kept the same. Alright. Now suppose I build this current mirror circuit, but in this extreme case I don't connect anything to the drain of M2. What happens here? What is the current I0 and what is the voltage V0? In fact, we've seen this before, so I'll just write the answer. Nothing flows. This is an open circuit, so no current can flow. So I0 is 0. And because no current flows, although this transistor is on, okay, let us recognize that because of IRF and M1, VG1 has a non-zero value, some value greater than VT. And because VG1 is greater than VT, M2 has a channel. If the transistor is on, it has a channel, but it is carrying no current. And if a MOSFET is on, but it is carrying no current, then the only way it is possible is that its VDS, the drain source voltage, is 0. So in this circuit, VO will be 0. What this also leads us to kind of realize or remind ourselves is that for this to act as a current mirror, that is for I0 to be equal to IRF, M2 must be in saturation. Alright, as soon as M2 goes into triode, the current I0 will not be equal to IRF. This circuit without anything connected to the drain of M2 is of course an extreme case of triode. So this M2 is in triode with a 0 drain source voltage. Alright. Okay. A question arises. This IRF, so we built this circuit to make a current mirror, but if we go back, and let me go back here, our purpose, the original goal of this mirroring was that we want ID to be invariant with process and temperature, ID of M1. So a question arises as to why not I just put a current source here, IRF directly? Why do I have to have a mirror? Right? I hope that question did arise in your mind before I just asked it myself. Alright, so how do we answer that question? Right, here is the question. The answer is that IRF is actually a very complex, elaborate circuit. Alright, it's not just one transistor, it's a very big circuit which is designed so that the value of the current IRF does not change with process, with temperature, and with the bias, the supply voltage. Alright, and so this is actually something you may see next semester if you take the advanced analog design course. Razavi in the second edition discusses the constant current these are called constant current references, and he discusses it in the 12th chapter, which is on reference voltage and current sources. So we will not discuss it here in this course, but we recognize that the circuit that makes up this constant current source is very complex, and because it is complex, it is not feasible to build an IRF, a complex current source, for every current source needed on an IC, because an IC may need hundreds of such current sources. So we cannot build 100 such complex IRF circuits. That is why mirrors are used. Alright, so in fact, I'm sorry, this should have been come before, but anyway, so this is not feasible because what I just said. Alright, so and again, we've discussed this before, but if I want a current mirror, so I'll need a current reference, and if the current reference is needed from VDD to a floating point, it will be a PMOS current reference, and if it is needed from a floating node to ground, it will be an NMOS current reference or a current mirror. Alright, so there are two types of sources and mirrors, PMOS or NMOS, depending on what is the requirement. Alright, so what is done then? How is so if I have only one IREF, and if I need 100 places where I need current source loads to be available, then how does the integrated circuit achieve this? So the way it is done is, in fact, so this circuit, one IREF and one transistor generates a gate voltage. That gate voltage tracks variations in Vt and mu n. Alright, so now this gate voltage, what we had done earlier was we had connected this gate voltage to M2. So not this circuit, maybe this is better. And then M2 carries a current I0, which is proportional to IREF. So now one can imagine that I can connect this VG1 to 100 different NMOS transistors which need to act as current sources. Alright, so instead of building a current source by providing a DC gate voltage to an NMOS, I will just put this gate voltage to wherever it is needed for the MOSFET to be a current source. And one achieves different values of currents, because if I have 100 different places where I need current sources, of course each current source will need to have a different value depending on the design of that specific amplifier or whatever. So the way one achieves different values of currents is, of course, simply by changing the widths, the relative widths of the reference transistor and the actual current source transistor. So this is how current mirroring is done. So with one source, many mirrors can be formed. Many mirrors will reflect the original current source with different values. Alright, now so we've built a current mirror, and we can think of this whole circuit, the 3 volt IRF M1 M2, and if I enclose this in a box, then that box itself is acting like a current source with a current flowing from VO to ground. And whenever we have a current source, we must be able to characterize and kind of give some quantitative measures of how good a current source it is. And there are two major parameters that are used to characterize these current mirror circuits acting as current sources. So one obvious characteristic of the current source must have is that its equivalent output resistance, or the Thevenin's resistance looking into the output terminal, must be as large as possible because it's a current source. So that is one measure, is the output resistance, the Thevenin's output resistance of the current mirror. The other is what is the voltage it requires to act as a current mirror. Alright, or I will use the words mirror and source interchangeably. So for an NMOS, there is a minimum output voltage below which this circuit will stop acting as a mirror when M2 goes into triode. And that minimum voltage for this circuit, of course, is the overdrive voltage of M2, which is VGS1 minus VT, which we've called VO1. Alright, and the output resistance of this current mirror is, of course, just the RO of M2, so that is RO2. So these two quantities characterize this simple current mirror. Ideally, of course, we want RO to be infinite, alright, and we want VO to be 0, VO min to be 0, because that will make the most beautiful and the most desirable current source But of course, in real life, neither is possible. But there are various circuits that have been designed that give us larger and larger output resistances. All right. It is impossible to reduce VO min below that overdrive voltage of this transistor. All one can do is make the overdrive as small as possible, and as we've seen before, the smallest overdrive one can design for is 0.1 volt. All right, so one cannot design a current mirror with a VO min less than 0.1 volt. But let us now look at a few circuits where we increase the R out. All right, so this was okay. I was going to ask you, but it's okay. So how can we increase R out? Now we already know that a Cascode gives a higher R out compared to a simple single transistor. So we say, well, if I want to increase R out of a current mirror, instead of one transistor, I'll stack two transistors and put the output here, and then my R out will be much larger, and we've seen this already. So R out is GM4 RO4 RO3 plus RO3 plus RO4. All right. So we say, okay, this I want this to be my mirroring circuit, but then I have to have the source which it is mirroring, right? So you have to provide some biasing so that IREF it gets mirrored to IO. So how do we convert this to a current mirror? All right, you think about it. So this is okay. So this is what I'm asking you to think about. So think for a couple of minutes or 10 minutes and then continue this video. All right, so the first thing we do is, of course, this is our mirror. This has always to be there if we are mirroring. So we say, okay, IREF, a diode connected transistor, and that gate of that diode connected transistor gets connected to M3 so that the gates as well as sources are connected together. So now this circuit acts as a mirror. IO will be, of course, equal to IREF. The output resistance now will be large, GM4RO4RO3. The only thing that is remaining is we have to bias VG2 also, right? There has to be a DC voltage connected to VG2 such that M3 is in saturation, and at the same time, we can't connect a DC voltage source here. Can we? Okay, that's a question I'm leaving with you. Can we connect a DC voltage at VG2 and that will make a good enough current mirror? All right, so I'm leaving that as homework. That is not done in most actual mirror circuits. So one bias technique that has been used for many years until recently, and we'll come to the recently in the next class. So is as follows. So how do we bias this M4? So here is a circuit that biases M4. So what we do is we stack on top of M1 another diode connected transistor. All right, and that diode, so IREF is forcing its current into M2 as well as M1. M1 and M3 are a mirror. M2, M4 are not a mirror because their sources are not connected together. But M2 creates a voltage which can be used to bias the gate of M4. All right, so this is the Cascode current mirror circuit. And as I said, this was used for many years. Now it has been replaced by another one, which we'll see after we discuss this circuit. Okay, so let us find its performance parameters. So we already saw that the R out is GM4 RO4 RO3 plus RO3 plus RO4. Let us find what is the minimum output voltage that can exist at this node while keeping M3, M4 in saturation. So if you just look at this, intuitively it would seem that the minimum voltage that would exist is the overdrive of M3 plus the overdrive of M4. So it will be 2 times if these two overdrives are equal, then we say this is 2 VOV1. But it turns out that actually this is not the VO min expression. So let us look at this circuit more closely. All right. So let us put numbers. Let us say that all overdrive voltages of all the 4 transistors are 0.2 volts. All right. And then let us find VO min, and we'll go through this route. All right, because in fact we need to go through this route rather than going straight up, and we'll see just in a minute why. So we say, okay, VG1 is equal to 0.2 plus the threshold of M3, and I'm assuming that the threshold is 0.4 for all the transistors. So VG1 is 0.6 volts, 0.2 plus 0.4. If this is 0.6, of course this is 0.6. And if this is 0.6, how much is VG2? We've done this before. In fact, so M1, M2 are, by the way, M1, M2 are also identical transistors, usually with the same W by L's. So everything is identical, same current is flowing through them. So if this VGS is VG1, this VGS is also VG1, right? So VG2 will be this voltage, which is VG1, plus another 0.6 volts. All right. So we say VG2 equal to 0.6 plus 0.6 equal to 1.2 volts. So this is 1.2 volts. Now, of course, similar to M1, M2, M3, M4 are also identical transistors. Same W by L, same mu and everything, Vt. Therefore, if the same current, and of course the same current is flowing through them, therefore if this VGS is 0.6, this VGS also has to be 0.6. So if VG2 is 1.2, then VD3, this node voltage, has to be 1.2 minus 0.6. So it has to be 0.6 volts. All right. So this is 0.6 volts. Now this is one overdrive. Therefore, VO min is 0.6 plus 0.2 equal to 0.8 volts. Oops. All right. So VO min is 0.8 volts. But we had thought that VO min will be actually equal to twice VOV, and VOV is 0.2. So we had thought intuitively that VO min should be 0.2 plus 0.2 equal to 0.4 volts. But when we actually analyze the circuit, it turns out that it is 0.8 volts. Now let us think about why this happened. All right. The reason it happened is because we have forced, I'm not sure forced is the right word, but this node voltage, the drain of M2 is at 0.6 volts, right? And the drain of M2 is 0.6, and this is another 0.6. So this is 0.6 and this is 0.6. So this has to be 0.6 also. So the question is, well, can we do something to bring this down to 0.2, which is the overdrive? All right. So that we'll do next time. All right. So this is the end of this lecture. Next lecture we'll discuss how to bring this VO min down to 2 VOV, and then we look at other current mirror circuits. All right.